Now, as we go on to the last section of Chapter 3, it's functions. And we're going to work with a relation, a domain, range, function, vertical line test, and function notation. Now, I've written this as a quick overview of some of the important topics in this section. Now, we have been dealing with the ordered pair. And we know that when we plot the ordered pair on a graph, that we do the x and we do the y. And these are connected to each other. So in mathematics, when we define a relation, we're talking about something that is connected. And a very good example of this is the ordered pair. That is a mathematical relation. Now, the word domain over here, interestingly, is the x elements in a series of elements. The x elements are the domain. So in the ordered pair, again, it would be what would be in that first column. And the range is the second element. So there's our relationship. X is the domain, Y is the range. And if you have trouble remembering this, which is which, alphabetically we have X, Y. Alphabetically we have D, R. So a little way to help remember. And then the word function. In mathematics, this has a very particular function. And an easy to remember definition of it is that the x element in a series of relations is only used once. If the x element is repeated in a series of relations, it's not a function. And we'll be going over a number of things to help you remember this, and this is just an overview of what we're going to be talking about. Okay, examples of a relationship between two quantities. Well, the area of a square is, area would be the y, equals x squared. So as we square the x, we get the y. That is a relationship. The equation in slope-intercept form, or even standard form, indicates a relationship. Online advertising revenue, as we show it through the years, is a relationship. That is, it's a connection between two quantities. Okay. So I have already defined what a relation is, and a domain, and a range. So in example 1, they want us to, in roster notation, find the domain and range of these ordered pairs. Well, basically what we're going to be doing for the domain is take the x element, 0, 3, -1, and if it's written twice, like it is here, a 3 is there and a 3 is there, we don't write it twice. We only write it once. Now the range would be the y elements, a 2, a 3, a 0, and a -2. Now notice none are repeated, so we would write all 4 of them. Identifying a function. Well, as they give us the example, the x element is only used once. So if we look over here, we see x is 0, 3, negative 1, 3. Here it's used once, and here it's used again. So the x element is not used only once. So this one is not a function. Let's go on. And determine whether each relation is also a function. Well, again, we look at the x element. Is it used more than once? So we have a negative 1, a 2, an 7, and an 8. Is any x element repeated? No. So this is yes. It is a function. Now here we have a 0, a 1, a 0. See, the 0 is being repeated, and a 7. So since the x element is repeated, this is not a function. Okay. So far it's easy. And again, hopefully you're taking notes. You want to develop something to look at as a summary and outline. And we can do this one too because it gives us a little more practice. 4, 3, 8, negative 5, yes. X is not repeated. 1, negative 4, 0, 1, yes. 1 is repeated, so that's not a function. Now, when we look at a graph, remember here the x value is negative 4, negative 2, negative 1, 1. Are any x values repeated? No. So yes, this is a function. Now as we go here, we see we have a negative 2. But when we get to the 1 here, we see we have 1 is used twice. So this is not a function. And again, you can read your textbook. I'm just going over it with you. And looking at this one, 3 is used twice, so no. Yes. Now, we also have another tool that's called the vertical line test. So what I'm going to do is have a vertical line, this red line here, that I'm going to move over the face of the graph. Now as I move that red line over the face of the graph, right over here, which is now the dotted line, which is my red line, it intersects there and there. So it intersects twice. Now, if it only intersects once as you move it over the face of the graph, it's a function. And we say it's passed the vertical line test. If it intersects more than once, it doesn't pass, and therefore this is not a function. That's called the vertical line test. It's sometimes referred to as the pencil test, moving a pencil over the graph, which the pencil is your vertical line. So we have some examples. Again, you're going to be moving this vertical line the face of the graph. Now, as this line moves over the face of the graph, does it intersect more than once? No. So this passes the vertical line test. So this is yes. Now, by the way, this is negative slope. So that negative slope is a function. It passes the vertical line test. Now, if it was positive slope, that too would pass the vertical line test. All right, now here we have an equation, y equals 1. It's a horizontal line. Does a horizontal line pass the vertical line test? And the answer is yes. Now here we have a sideward parabola. Does this pass the vertical line test? No, it's intersecting in two places. So this is a no. Now how about the vertical line, which is x equals 2? Well, when the vertical line comes over this, it intersects in an infinite number of places. So this is no. So we're thankful, something relatively easy. And these, positive slope, let's just do these. This is yes. Now, whether our parabola opens upward or downward, it also passes the vertical line test. Horizontal line, wherever it is yes. But a circle, no, because it intersects two places. Okay, now they're asking us to look at formulas and decide whether they describe a function. Well, if you can kind of imagine the graph of these, let's do the graph of A. That's going to be a line that looks like so, because our slope is 1. Our y-intercept is 0, so it goes over 1, up 1, and that is a function, so yes. This is another equation where our y-intercept is 1. Our slope is 2 over 1, so we go over 1, up 2, and that is yes also. Now this is the graph of a horizontal line, 1, 3, 4, 5, going through 5, and we said that is a function also. Now here, this is a graph of a vertical line going through -1, and all vertical lines are not a function. And here, this is yes, this is yes, this is yes, this is a horizontal line, vertical line, no. Now it's a little tricky when you have a parabola, but they're not giving us those, so we'll stay away from that right now. If they do, we will address it. Now, another example of a function can be found in magazines, newspapers, books, in the form of a table graph. This graph shows sunrise times for the year. Use this graph to answer these questions. Okay. Approximately the time of sunrise on February 1st. Well, this is February 1st here. We go up here and we go over there, and I don't know, what is that, about 7? Is that on the graph? It's kind of hard to make out, but if it's right on there at 7, that would be 7. Approximately when does the sun rise at 5 a.m.? Well, you go to 5 a.m. here. And here we're getting, let's use a little line here, because that would help. Oop, went back there, 5 a.m. here. So approximately May and in August at 5 a.m. And that's what you're doing. You're seeing where it is and then matching it up to the side. And I believe you do have this in your math lab here too. And they're doing what we said here. Okay. And there's practice, which is something similar. Okay, I guess I had to go back there. And function notation. Yes, I missed this. Well, when we are writing function notation, we can start with, let's say, y equals mx plus b. This was formula 2. And this y equals this in slope-intercept form. Well, we can modify the y by changing it to function notation and saying f of x is equal to mx plus b. We have gone from our graphing mode and the typical slope-intercept form to a function form by introducing f of x. And then what this x here in parentheses refers to is a value for this x here. So this is often shown sometimes using a machine of some type that's going to be in this box. We're going to put in an x value into the box, which is this expression here, work it, and what comes out of the box is a y value. And we use this throughout chapter 3 when we made our t-charts. We were putting in here x values, a -1, a 0, and a 1, and we were getting out y values. Now, a way to look at the x here is, here this is an independent variable. It's independent because we are putting it there and saying it's -1. It's independent. Now, by putting the -1 into the machine, this formula, it comes out as something. So depending what goes in, the independent, we get a value that comes out that is the dependent variable. We often refer to this as the input and this as the output. Now, these are illustrated often many different ways, but basically that's what they're talking about here. Okay? Now again, I didn't read the text to you. That you can do on your own. And we've covered what we want to there. Let's give an example here. Now, here we're given function notation, and let me write that out for you. We're saying, and by the way, you could use other letters other than an F. So g of x is that x squared minus 3. Now, when they ask us these values to replace the x, we go to this function that includes the g. I would make a t-chart. And then here we're going to put g of x, which is actually, remember, a y. You can always substitute a y for function notation. And what values do they want us to have? Well, they want us to have a 2. They want us to have a -2. And they want us to have a 0. So we can do it written out, or almost these we can do mentally. 2 squared is 4. 4 minus 3 is 1. -2 squared. Now remember, that's in a parenthesis. That's also a 4. Minus 3 is 1. And then if x is 0, 0 squared is 0, and we get a -3. Now notice they're giving you the values this way. I think it's nice to think of it this way. These are, in a sense, an ordered pair, and your T-chart helps you to organize what you're doing, and it ties it in to what we have been doing in this chapter. Oh, and a little note here, that whenever you see f of x, it's f of x. It does not mean that the f is times the x. This is just function notation. Does not imply multiplication. They're going to give you some value of x that you put into the machine, which is the formula, and then you're going to get an output. Okay, and you'll be practicing this as well. Going on to example 8, here we're going to take a look at what is the domain of each of these functions. Now, when we say domain, we're looking for values of x. So as we look at example 1, what values of x can be found in the denominator? Well, can 1 be there? Yes. 2, 3? Absolutely. But how about if x is a 0? That would be undefined. So when we are looking for the domain of something in which a variable is in the denominator, we have to exclude any value of x that would make the denominator a 0. So we just equate usually x equals 0. Well, if x were 0, that would make our denominator a 0. So what is our answer set then for letter A? Well, x is equal to any real number, but x cannot equal 0. Now they want the answer given in interval notation. Well, let's make a graph of what x would be like. Well, here's 0, and at 0 there would have to be a hollow, and then this would all be filled in for the other real numbers. So how do we write the interval notation of that? Well, it's starting out here at -infinity, going up to 0, but stopping just before 0. And then we use this union symbol that we haven't had yet, but I'm giving it to you now. And it's going to go from the other side of 0 up to +infinity. So that's the answer for A. Now when we look at letter B, we see that this is just a straight line. The denominator is just 1, so there are no restrictions to what x could be. So x would be all real numbers. And we would say from -infinity to positive infinity. And they have it all written up down here. Now, doing this one, again, there would be no restrictions. Negative infinity, positive infinity. And here, again, the only restriction would be if x were 0. All other numbers would be good, so it's the exact same as this one here. Now, for number 9, they want us to find the domain and range of each function graphed, and they want to use interval notation. So for a strategy here, remember our domain are our x values. Well, what we do is we take our graph and project it to the x-axis, which is right there, and then this down to the x-axis, which is right there, and in a sense, that's our graph. These would be our x values involved in this function. So, in interval notation, since -3 is included in the set, and then up to 4, which is also included in the set. Now for the range, we can do the same thing. As we look over here, our y value is a -1, and this y value is a 5. So it will go from and including -1 up to 5. Now for this parabola, our x values, and in a sense, since this is sort of swinging off here, I'm exaggerating it a little bit, will include all of our x values. So our domain here is from -infinity to positive infinity. Now our range starts here at -2 and goes up to infinity. Okay, that one was a little bit easy, but bringing some memories back. And we'll do this one too. So we know the procedure. It's going to be domain is from our -4 up to our 6. And range is from -2 up to 3. All right, now for this one, again, our domain will be from -infinity to positive infinity, and our range is coming up now from -infinity up to 3, and 3 is included. And that ties us up.